We're just about there. Welcome back, everyone, so far. And it's official. We can get started. Closing out week 4. One nice bit of information about the semester is we're at the 25% mark after class is over today. So hope your other classes are going well. For this class, I intend to have the exam one graded over the weekend. I'll begin grading it on Friday, but I gave 2 exams this week, and I usually go in order. Gave an exam on Monday. I'm going to start with that one and then move into our exam right after. I hope to have it completely graded by Friday, but if it takes me a little bit longer to get it completed, I'll have it done on Sunday evening at the latest. You might have noticed that's kind of like my catch-up day usually, to try to just cram things in, getting everything graded up. For people who took the class or people who are taking the class in the online section, watch for your ISU email address. I'll be emailing you back a hard copy or, well, a scanned PDF copy of your exam. And if you're in the in-person section, I'll be handing you back a hard copy on class on Tuesday. But if you're in the in-person section and you want your exam back earlier, just send me an email and I'll be happy to scan it and get that copy to you sooner. So if you're dying to know how you did, I can get that to you faster. Check your grades after the exams are graded. I'll probably make an announcement on the Canvas page so that you don't have to check like a million times over the weekend. You can wait for the announcement, which I believe sends you an email to your ISU email address. I'll have your exam graded there and your overall course grade with everything put together. So that's our plan so far. For today's class, we're returning to section 1.5, which was extremely rudely interrupted by the fire drill. Sorry for those people in Zoom as well. The fire alarm went off, and I think I just kind of panicked for there a second. I thought I said class is canceled. We have a fire alarm, but I don't think I even said the class is canceled part. Just kind of closed Zoom and ran away. I happen to spend a lot of time on the internet satisfying my morbid curiosity on fires. They're scary things, so I took it pretty seriously. But we'll finish off section 1.5. The due date's going to be a week away from today. And we'll probably make some progress into 1.7. But any questions at all, folks, before we get started then? Okay, so here's not quite where we were, but it's been an entire week. So here's the refresher. The core definition in section 1.5 is about the homogeneous equation. The equation is homogeneous, whether it's a matrix equation, a vector equation, or an ordinary system of linear equations, when you have it set equal to 0 as a matrix equation or a vector equation, or all the right-hand side equations as a system of equations are all set to 0. Key fundamental fact about a homogeneous system of equations is it always is consistent. No matter what, it'll have the so-called trivial solution. That's the 0 vector. And you can see how if you did put it in 0 vector here, did the matrix multiplication, that's just a linear combination using 0 as scalars for every single vector, pairing up with the columns of A. So you automatically satisfy this equation just immediately. Major thing we want to discover is when will there be non-trivial solutions? We found in our discussions that's going to happen through this theorem too, the moment you find at least one free variable. So a free variable tells you non-trivial solutions exist, which also is going to tell us something interesting about the columns of that matrix A. So here's a problem that we did before the fire alarm. We were wondering if this had a non-trivial solution. The augmented matrix is presented, and it meant it's a homogeneous system set to the 0 vector. When we row reduced, x3 was free. So we knew right away there are non-trivial solutions. And in the very next section, 1.7, that'll tell us something about the columns. The columns are linearly dependent. So we kind of redid this kind of concept here while we were attempting to. I think we just stopped mid-thought on this. This is when the fire alarm hit. We were looking at this system and we observed it's homogeneous. It was asking, is it possible for it to be inconsistent? And we said, no, it is consistent because it has the trivial solution which is x1 equals x2 equals x3, all set to 0. Or you could just say x equals a 0 vector with 3 entries, all components x1 through x3 set to 0. So that's kind of our recap so far. Any questions about the new terms and ideas in this section so far? Okay, well, in the last matrix, we found that there are non-trivial solutions. When we looked into the matrix equation, it already was augmented with the 0 vector. And this is the same kind of question, except there's a additional parameter, that value of h. So this is kind of like our third or fourth question, kind of along these lines. We want to know what value can you put in for h so that there will be non-trivial solutions. What value or values for non-trivial solutions? First thing we want to do is solve. Let's say this better, not quite solve. We want to row reduce the augmented matrix for ax set equal to the 0 vector. The 0 vector here is going to be the right-hand side, so that's what we're augmenting. When it says a, that's just going to be the coefficient matrix coming from, or gathering up, all of these coefficients, with the understanding that if I just highlight x1 like that, the coefficient is a 1. So the augmented matrix would look just like this. Go 1, 2, -1, 2, 5, 1, 1, 3, h. So we pulled all the coefficients out of the system of equations. That's the a side in the matrix equation. Next, augment with the 0 vector. That's the right-hand side of the equation, whether you're looking at the system or the matrix equation. And it always kind of looks weird when you augment like this. You wonder, where did x go? But this is x1, x2, x3 information going this way. And so now we just want to row reduce. And I forgot to put in one thought here. Row reduce it to echelon form. You've noticed probably already that a lot of our methods really just comes down to this kind of work. Find out what kind of matrix to write in, how to augment it correctly, and just take it to echelon form. So let's do the nice relaxing work of row reduction. We're probably starting to become experts at this kind of thing at this point. Row 1 can copy in as 1, 2, 1, 0. Take -2 times row 1, add it to row 2, and we get 0, 1, 1, 0. Next, just take row 1, directly add it to row 3. We'll get 0, 3, h plus 1, and 0. So now we've revealed 2 pivot positions, one here, one here. We need to eliminate the entry 3 below, so that's our second row operation. Copy in first the first 2 rows, 1, 2, 1, 0, 0, 1, 1, 0. 0 there, can't change. And next operation, multiply row 2 by -3, add to row 3. We'll get 0 here. This one's going to be -3 plus 1, so h minus 2. And still augmented with the 0 vector. So we have pivots here, here. I don't necessarily want to circle this one because if it's a pivot position, well, that depends on the value of h. For most values of h, it is a pivot. But for exactly 1, we lose that pivot position entirely. And that's what we're trying to do. We're wondering, what can h become so that there are non-trivial solutions? This is where the ideas and definitions start to really connect a whole bunch. If we start on this side, non-trivial solutions, we can say non-trivial solutions. This will happen if and only if, so there's that biconditional arrow there saying the logic goes both ways. If and only if there is a free variable, And that will occur if and only if, how will we get a free variable? That just has to be 0. So we'll say h equals 2. And just because we haven't used this notation a ton, let's just redefine it here as a warm-up. This means if and only if. In other words, the logic goes both ways. Non-trivial solutions will occur if and only if there's a free variable, if and only if h is 2. Or we could say, in other words, h is 2 implies there's a free variable, implies there's a non-trivial solution. We can work the logic forwards and backwards now through this biconditional arrow. So that's one way to answer the question. Any questions at all, folks, with this one here? Okay, so why would we want to know about when there is a free variable? Well, if this system came from something physical, some kind of maybe a chemical equation, or maybe analyzing forces on a bridge, you would want those columns to be linearly independent, potentially. And it might be interesting to know if you change one key part of the model, there is a bad position here, which is going to force linearly dependent columns. That might be problematic for dealing with solving these kinds of systems later on, or dealing with what's going on with your model. So that's one reason why we care about these kinds of things. Another bigger reason about all of this is, like we mentioned, this will tell us as well when h is 2, the columns are linearly dependent. So that's going to be our conclusion really just in the very next section. For the moment, we're just mainly focusing on having the non-trivial solutions. Well, we'll look at a couple more kind of problems along these sort of lines. Next thing we're going to be interested in is some interesting theorems that are going to just make this process really, really fast all at once. We looked at some of these kind of ideas already when we were taking a look into a matrix equation in the prior section 1.4. We noticed in section 1.4 that if the size of the matrix is just right, say if n is greater than m, you can say something about free variables just instantly, which is going to tell you if there's infinitely many solutions or a unique solution just based on that kind of information there. So to tie this together, recall that m is number of rows, n is the number of columns. So if n is greater than m, then you have non-trivial solutions, and all your work is pretty much done. That's a nice theorem because now it tells you if this was the right size system, if there was, say, an x4, you didn't have to do any of this. You would have just said, well, there's 4 columns in my matrix, only 3 rows, guaranteed to have non-trivial solutions instantly. Row reduction is not even a part of that problem any longer. Another way to kind of view this is you can think of the matrix A augmented with the 0 vector. So that's this part right here, looking a bit like this. Say we have just a dot here to say some undetermined entries. I'm writing out with 4 rows. Going for 5 columns, just so that we don't have to have too many dots. Then augment. These are definite positions of 0, 0, 0, or definite known entries. We have 4 rows, 5 columns. So now we can connect a dot, similar to, again, thoughts that we were thinking about in section 1.4. At most, there would be a pivot here, here, and here. So we can say there is at least one free variable. But our prior theorem told us the moment you have a free variable, that will imply ax equals the 0 vector, and painted myself in a corner there, has non-trivial solutions. So that's the kind of visual way to think about this theorem. Does that make sense to folks so far, how to work this theorem? Okay, so if you have simply just more columns than rows, you're guaranteed to have at least one free variable. If I had 6 columns, I would have said at least 2 free variables, and so on. So putting this into practice, here's another system. It says the augmented matrix is this one. Just for emphasis, that means that's not the original matrix A. We have that A is 1, 8, -3, 1, 7, 1. We're to determine if the system, whose augmented matrix is this, has a non-trivial solution. We have to justify our answer or just explain our work. We can't just say non-trivial solutions and call it good. But there's really not a lot to say. In view of the prior theorem, you might just simply say there are 3 columns and only 2 rows. You might connect the dots as well. You might say there's going to be at least 1 free variable, maybe exactly 1, potentially 2, not 3. If there's 3 free variables, then that'd be a zeroed out matrix. But you could just use the theorem and go to the punchline. Now that you know that there's a free variable, automatically there are non-trivial solutions. Our work is done. Let me say this in kind of a more parallelized way. So this means, by the last theorem, there are non-trivial solutions. And our job is done. I mean, row reduction wouldn't have taken too long, right? But you can imagine maybe this is a 4 by 11 matrix. You wouldn't necessarily want to do any row reduction on it if you don't have to. You're guaranteed to have a free variable, which means the homogeneous system is also guaranteed to have the non-trivial solutions. And, it doesn't hurt to emphasize when we say there are non-trivial solutions, we mean non-trivial solutions to AX equals a 0 vector. That's the actual equation that we're considering. Not a bad thought to connect in your mind each time you're thinking about non-trivial solutions. Probably the next questions folks would have is, what if we wanted the non-trivial solutions? That's an important part of linear algebra as well. And so far in these notes, we haven't done any computations along those lines. We've just learned how to detect if they exist, not how to actually get them. And that's what the next problem is going to be all about. I made a couple remarks out of the importance of this, and I also screenshotted the homework assignment before class started today, just as an extra reminder for the importance of this technique that we're about to do, the parametric vector form. If something is bold and it's at a higher point font and highlighted in yellow, that's at your kind of a dead giveaway. This is one really big important aspect of linear algebra. In fact, just to emphasize it, this is as important of a concept as the span of a set. And we keep mentioning these same sort of things. When we get into, say, chapter 4, chapter 5 work, understanding the span of a set and understanding parametric vector form is going to be used a lot for things like null spaces, column spaces, eigenvectors, eigenspaces, and so on. Getting foggy on how to do this makes all of that work feel like you're doing some kind of foreign language out of nowhere when you thought you were doing math. Looks like we're studying, say, Mandarin or something. So that's what these remarks are about. A fundamental technique that we'll use a lot in this course is getting the parametric vector form to a matrix equation or a system of equations. And when we do that, this time echelon form isn't going to do it for us. We have to reduce all the way down to row reduced echelon form, or reduced echelon form for short. Really, this is a problem that we could have done in section 1.2, maybe even 1.1 if we were just feeling brave. But now that we have all the vocabulary we have so far, this is a good time to take a look into just how to do this. So in other words, we're going to find the entire solution set, not just the trivial solution, but also all of the non-trivial solutions when we do this. And for full credit on homework assignments, problems 5, 8, 11, we're going for this exact form. If you forgot to do this on your homework problem, I might go like -3 in blue and then just tell you, put in that work and I can accept it for full credit. It's that important that I would allow a retry on that kind of work. So first thing we're going to do is write down the augmented matrix for, let me pen catch up, the augmented matrix for AX equals the zero vector is, A is the matrix of coefficients from the left-hand side of these equations. So pole coefficients, we have 1, 2, -1. Going column-wise, then 2, 1, 1, -3, -3, 0, augmented with 0, 0, 0. Just for notational help, we have variables x1, x2, x3 associated with those columns. Then we start the row reduction. Copy in row 1, 1, 2, -3, 0. Multiplying row 1 by -2, adding to row 2, it's going to give us 0 here, -4 plus 1 for -3, +6 minus 3 for a +3, and 0. Next, take row 1 added to row 3, and we'll get 0, 3, -3, 0. So it's coming along nicely. We have zeros below that pivot. Next pivot position is right here, but in reduced row echelon form, that's got to be a 1, and we need zeros above and below. Just so that we're not doing like 4 or 5 row operations at a single time, I'm going to divide that row by -3. So 1, 2, -3, 0. Now divide by -3 in row 2 to get 0, 1, -1, 0. And if you wanted to divide by 3 in row 3, you don't have to, but that makes it look nicer. 0, 1, -1, 0. And we're off to our next step. Oh, but I divide it by a -3 altogether. So I got a +1 and a -1 on that one. And really the only reason I went for +3 is we just wanted strictly a +1 in this position.
Oh, yeah, okay.
But other questions so far? Yeah.
If you wanted to bottom one by -3 to give yourself -1 ahead of time to that way you just know it ends up in 0.
Yeah, actually, I like that. That's a great suggestion. I divided by 3 just because it just seemed okay to do that. But by the suggestion in class, let's go with that. Divide row 3 by -3. Now we're not doing as much row operations as once. We will get -1, 1, 0. And that just looks more satisfying, right? You're just adding those 2 rows together. So yeah, I think that's a great way to do this one. Other comments at the moment? Okay, so we've got pivot in column 1 squared away. A pivot here in column 2, we need to eliminate entries above and below. So next thing we probably want to do is just copy in row 2 and row 2 alone. 0, 1, -1, 0. Let's fix row 3 now. Take row 1 added to row 3. Everything is now going to a 0 down below. We made it easier on ourselves. That was a good strategy. 0, 0, 0. Now we're eliminating this entry above. So multiply row 2 by -2, add to row 1 to get 1, 0. This is +2 minus 3, so -1 again, and 0. We're done. We have a pivot here, a pivot here. That pivot corresponded to x1, x2, which means in this system, x3 is the only free variable. This one has non-trivial solutions, but what we want is a little bit different. We're going to just write down the whole solution set to this. One thing that seems kind of weird is we kept carrying in this 0 column vector. And we know it's never, ever going to change in these row operations. But one of the reasons for it being a good idea is it's all about bookkeeping. This is a nice reminder that you have an equation set equal to 0. So if we translate this system back to a system of equations verbatim, it's going to look like this. X1 minus X3 equals 0. And then in row 2, it's going to be X2 minus X3 equals 0. There's no information in row 3. You could write 0 equals 0, but it's unhelpful. But you should say something about X3. One thing you could just say is X3 is free. But in parametric vector form, we actually need something a little bit more to get to where we would like to go in describing the solution set. So this is a good step to take, but we also mentioned oftentimes we do a shortcut here. This is what the shortcut would look like if I never did the step in the middle. It's a good shorthand to save you lots of writing. You could just say, well, this is x1 minus x3 equals 0. So just solve it for x1. x1 equals x3 by adding x3 across this dash line, which is just literally an equal sign. x2 minus x3 is 0, so we can say here x2 equals x3. And the next idea is when we said x3 is free, again, not the most helpful thing to say. It's actually a little bit helpful to say this, x3 equals x3. And that seems weird because that's not giving us any interesting information other than it's reminding us that x3 is a parameter. There's no restriction on it. You can choose a value for x3, and it's determined x2 and x1. So we're still not at parametric vector form. This is where we usually ended our solution set when we're doing this in the 1.1, 1.2, 1.3 homework. Finally, parametric vector form is going to look like this. The parametric vector form for the solution set to AX equals the 0 vector is X equals. We're going to take a couple steps on this. I'll circle or box out the part we're really going for. But fundamentally, X is X1, X2, X3. That's all this X is right here, just a listing of variables. But from this, we know what X1 is. X1 is X3. We know X2 is X3. And I made a mistake down here. Subscripts are sometimes easy to mess up. That should have said an X3 down below. And that's where this equation comes into play. X3 is equal to X3. This is still not there. We do one more operation, or maybe a set of operations. We have to undo all scalar multiplications. We have to undo all vector additions. Here, there's just a scalar multiplication we undo. And once we do that, we take x3 times this constant vector, 1, 1, 1. I often write x3 in R to remind myself it's a parameter. It can take on any value. And this is the so-called parametric vector form. I don't often box the answers, but I want to emphasize that's what we're going for. It needs to be written in that specific form. We're trying to reveal the constant vector. In the right context, that's going to be called an eigenvector later on. And this constant vector is the main punchline to why we want the parametric vector form. But any questions, folks, on going from what we did here in sections 1, 2, 1, 3 down to that expression? Okay, so we mentioned parametric vector form is a huge concept. And this is kind of like a warm-up question. We'll do one in a bigger system where there's more free variables, a lot more going on. We said it's just as important as a concept as the span of the set. But if you really think about what a span is and you stare at that long enough, that is literally the span of a set. So let's connect that thought as well. The solution set to AX equals a 0 vector is the span of that constant vector, 1, 1, 1. And when we write out the span of a set of vectors, we're not interested in putting out x3. That's if we're just writing it out literally what it is using set builder notation. We're just spanning this. It's a line in the x1, x2, x3 plane that goes through the origin 0, 0, 0, goes through the point 1, 1, 1, and it just extends infinitely in both directions. So all solutions to this equation, ax equals 0, is generated by spanning this. Contains the trivial solution, the origin in the x1, x2, x3 plane, and every other point, including this one, that goes through those 2 points in space. So we did it, folks. That's parametric vector form. We'll see a lot more about why it's so important, but really the big punchline is we separate even out the scalar x3 because what we want is the constant vector 1, 1, 1. Any questions at all getting through any of these ideas at the moment? Okay, let's try this out. Same kind of setup, but for a larger system. Maybe not a system of equations each and every time. We're just practicing seeing things different ways. On this next one, we're jumping down to this. Describe all solutions to ax equals a 0 vector, so another homogeneous equation, in parametric vector form. So this is the major thing we're studying. Where the matrix A, they've done some algebra for us, is rho equivalent to that. Not as much as we'd like. There's not all the row reductions we would probably want. Notice there's an entry here and an entry here causing problems. But another thing that's kind of dangerous about this problem is this is not the augmented matrix. I mean, it's missing the 0 vector. Is that a problem? Not exactly. You can go ahead and just row reduce this to reduced row echelon form. You can describe the solutions just fine. You just would have to remember that there is a column right here when you go to this step, or if you do the step in the middle. If you forgot that, you might get easy to get mixed up. What are the actual variables here? There's an x1, x2, x3, x4, x5, and an x6 in this. So including the 0 vector, it's always going to be optional for you. But for me personally, and in the notes, I'm going to put it in because I feel like it gives a lot of clarity. It's just really careful bookkeeping, essentially, by doing this. And a lot of math is just being organized so you can see where things are and connect the dots. So ax equals 0, we can say has augmented matrix. This is kind of a painful step because this is a big system. First, I'm going to put down just the variable. Here's A augmented with a 0 vector now. Now let's write it out. Because I'm just writing it out, we get to use equality here. This is literal matrix equation now. Copy this in, so this is the tedious part. Maybe row-wise is going to be the easy way. I'll have 6 zeros from the matrix A and a 7th one from where it's been augmented. So 1, 2, 3, 4, 5, 6, 7. That's where it's augmented. Then I'm needing, looks like 5 zeros, a 1 and a 0. 1, 2, 3, 4, 5. Here's the 1 and a 0. 3 zeros, 1, 4, negative 6. A 0. Then 1. Negative 2, 3. Negative 6, 5. 0 and 0. Okay, slightly tedious, but again, it's just for the sake of organization, because this is a lot of information to put together. The reminder is we have an x1, x2, x3, x4, x5, x6 variable in this system. And for equations, 6 unknowns. We already know immediately that there are non-trivial solutions to this because they're just as immediately, you might have spotted them three free variables. This is a pivot, this is a pivot, and so is this one. So we have x2, x3, x5 are free variables. That means when we go to describe our solution set to this, it'll look awful like this one up here by the red dot. X3 was a free variable, so it went right there. But this time we're going to have x2 times a constant vector, x3 times a constant vector, plus x5 times a constant vector, all added together. So we'll have a span of 3 constant vectors altogether if we just try to describe our solution set this way. Next thing to do is fully row reduce this to row reduce echelon form. And if you ever did this on a homework problem, an exam problem, just literally erase something and put in the 0, I'm okay with that. This is a painful one to copy step by step. I won't do it here because it makes the notes impossible to read. So let's do this tedious work. There's some shortcuts you could take here because this pivot position where the red dot is currently only has zeros to the left and to the right of it. That means it immediately makes everything above and below 0 without changing anything else. But if I did this in the ordinary way, I would copy in row 2 to start. That's 3 zeros. 1, 4, -6, another 0. My goal is to eliminate the -6, so I might as well just copy everything down below just so it's there. 1, 2, 3, 4, 5, 1, 0, and then all zeros. It's too bad they didn't complete the row reduction on this problem. It said A was row equivalent, but then they stopped at that step. Now here's my operation. Well, the first 3 entries cannot change because of the zeros below them. 1, -2, 3. 0 on the far right can never change as well. Now we're taking 6 times row 2, adding to the row 1 above to get 0. 24 plus 5, so 29. -6 times 6, so -36. And that's our new system. So here's the pivot analysis. We have one here, and this pivot column is completely done. Zeros above and below. Next pivot is way over here, but it needs some work. I have to eliminate those entries. Once again, a great shortcut here is because there's only zeros to the left and to the right, this stuff is just gone. 6 times row 3 added to row 2 eliminates it, and nothing else can change out here. 36 times row 3 added to row 1 eliminates this. Nothing can change here once again because of all those zeros. So if you erase this and just put in 0, 0, that's okay. That's acceptable. Again, it makes the notes cryptic, so let's take this one last step. 1, 2, 3, 4, 5, 6, 7 zeros. Let me try and make this a little shorter to fit the x1s through x6s. Then 1, 2, 3, 4, 5, a 1 and a 0. Then 0, 0, 0, 1, 4. And this entry is now 0. 0 again. Last one goes 1, -2, 3, 0, and 29. Here's the row operation. This one eliminates the -36 above, so it's 0 as well. And let me fix that size of this matrix one more time. Finally, we're ready to start. We have x1, x2, x3, x4, x5, x6. We have a pivot here, here, and here. The rest are free variables, like we said. So let's take that shortcut. It's kind of painful to write down these equations twice because there's so much going on. So let me know how this looks. I'd read this off in my mind as x1 minus 2x2 plus 3x3 plus 29x5 equals 0. But what we're doing is we're solving for x1. We want to solve for the basic variables in terms of the free variables, x2, x3, x5. So another way to read this is that x1 equals 2x2, because we're adding 2x2 to both sides of the equation, minus 3x3 minus 29x5. Does that make sense to folks so far on that row one? Okay, it's a gigantic time saver. So we're still reading out the equation, just like in this step, but we're just skipping over to here, solving for the basic variable. Then do it again on row two. We go all the way to the pivot column, and we're solving for x4 now. You know, before we do that, let's pause here for a moment. It's a good idea to do things in order. Sorry if you're writing in pen. You should really put down the free variable first. x2 equals x2, and we'll see why in just a moment. Organization is the big thing about parametric vector form. So let's put down things in order. Reason for that is when we go to this step, we want to say something for x1, x2, x3, so it can go to the right in a consistent way. We can't mix up these rows whatsoever. So being really methodical, let's do each variable in turn. I would write x2 equals x2 because it's free. x3 equals x3 because it's free as well. Then go down to x4. x4 equals, subtract 4x5, and nothing more to say, zeros throughout. Now we're on the x5 variable. We'll say x5 equals x5. Come down here, we're on our last variable, x6. But this is literally an equation 1 times x6 equals 0. So I'll just write x6 equals 0. My goal is to write this as a straight column, but I guess there's a little bit of drift here. Maybe too much coffee is a blame. But from this information, we can come back here and reconstruct x. We're just a step away from parametric vector form. Any questions at all, folks, with where we're at so far? Okay, so finally, we're going to take x. This is the solution to ax equals 0 right above here. So save x as this one. Let's connect the dot just because that's helpful as well. What is x? Well, A was a 4 by 6 matrix. The only way matrix multiplication works here is if there's 6 entries. x1, x2, x3, x4, and I underestimated the size of 6 entries, x5, x6. But we just happen to know exactly what that all is. It's this stuff right here. The step I'm about to write down is a kind of an optional one, but it's a good one to do for the first few times you're doing this. Just it's a connecting the dots kind of step. x1 is literally 2x2 minus 3, x3 minus 29, x5. x2 is just x2, x3 is equal to x3, x4 is negative 4, x5, x5 equals x5, and x6 is 0. Almost there. So this entire column vector that we have here is the result of vector additions and scalar multiplications. To get back down to parametric vector form, we're undoing all of it. But this is what it's going to look like. Notice what the free variables are doing. They appear here, reappearing here when we wrote those equalities. And the next thing we were going to do is make them appear over here. This is finally the punchline. This is our parametric vector form. The free variable x2 is just a scalar multiplying some called vector. x3, let me match the color coding, is doing the same work. It has its own coefficients. x5, same idea as the last. And all we have to do to undo all the vector additions and scalar multiplications is pull these coefficients. So coefficients for the x2 free variable will go inside here, And they are 2, 1, 0, 0, 0, and 0. So 2, 1, 1, 2, 3, 4 zeros. Make sure you have 6 entries to match up the size of this vector here. And that's literally all we're doing. Much of linear algebra is just pulling coefficients, like we mentioned. That's exactly what we're doing here. Now do it again for x3. Coefficients go -3, 1, and then nothing else for x3 after that. Let me try to put this better in line. Organization is really key here. X3 is in row 2, so it should look a little bit more like that. Then row 3 is a 0, 0, 0, 0, likewise for 4, 5, and 6. 1, 2, 3, 4. Almost there. So now it's for x5 coefficients, -29. Nothing in place of x2, so 0 here. x3, we have nothing in that position as well, so 0. x4, you might be looking over here where it's slightly better arrayed. x4 does have a coefficient, -4 times x5, so -4 goes here. x5 has coefficient 1 here, and then 0 down below. Because it's just x6 equals 0, there's only zeros below there. And this is how we pulled all those coefficients. If we really wrote them in, that would look weird, but it might help connect the dots. If we put in a 1 every time a 1 occurred, this is where all these coefficients came from. Then, if you like, you can say one additional comment where x2, x3, x5 are in R, any scalar whatsoever. So that's the parametric vector form for this system. Had a lot going on, so organization was probably the main thing that we had to worry about. But really, if you left it in this form right here, it's okay to go from here down below. You're doing the same exact thing as what we did over here. This is just to see how connecting x1 through x6 gets us to that spot. We're using the equations over here on the right. What we did, folks, is kind of a nastier one. Let's see if we can zoom out to see the whole problem. Not easily. Any questions at all getting the parametric vector form here? Yeah. Oh, you're right. I moved it up because I thought it was out of position, but no, absolutely. Good eye on that. It was x3 equals x3, and also that's where it came from here, just from it being a free variable. Let's make that correction right away. And that's what I was mentioning before. If you're organizing this just right, it's supposed to help you, but if I move things up or down too much, it's tricking my eye at that point. Should have been x3 here with a coefficient of 1, which makes a change on this position. That was a 0, matching the 0 entry right here. x2 didn't have anything for x3. And then a 1 goes right here. x3 equals 1 times x3, and so here it is. 1 times x3 like that. Thanks for spotting that one. That was an error I don't think I would have saw on my own, rereading my own work. Other questions at the moment?
We only use this form as the variable.
This could be used in this, yeah, that's a right thought, absolutely. If there are no free variables, we get a unique solution, just one constant vector. So yeah, that's the right thought. You have to have free variables to get to this parametric vector form. It's another question that could go along with it is, every time we've done this, there's only been a 0 vector, but there really could be a constant vector here. So sometimes parametric vector form could look like this. There could just be some additional constant vector here if the right-hand side wasn't all zeros. But we're doing it in the case where the right-hand side is only all zeros. So we never had a constant vector on its own without the free variable multiplying. Other questions at the moment? Then again, if you look at the definition of span really, really closely, this is nothing but a span of a set. The span of a set is the set of all possible linear combinations. And this is all possible linear combinations of these three vectors because x2, x3, x5 had no conditions. They can be any scalar whatsoever in R. So if you call this a V1, a V2, and a V3, where V1 is just the constant vector, not including x2, we can say AX equals a zero vector has solutions span, let's just write out to emphasize span 2, 1, 0, 0, 0, 0, -3, 0, 1, 0, 0, 0, and last is -29, 0, 0, -4, 1, 0. So the span of these three vectors, if you wrote out what that set looks like, it's literally just this. The scalar multiplications, vector additions, and no conditions on the scalars. I never actually used V1, V2, V3, so that's a good one to erase if you don't actually use it. So parametric vector form is really just looking at the span in a specific way. This is what we're going for. We'll try out a couple more concepts on these notes and then take an early look at what's going on in section 1.7, maybe run a couple problems. So next thing going on in these notes is theorem 4 from section 1.4 just makes a showing out of nowhere. The reminder on this theorem is it's a set of logically equivalent statements. In other words, A occurs if and only if B occurs, B occurs if and only if C occurs, C occurs if and only if D occurs, and D occurs, just kind of hard to convey this, if and only if A occurs. So we have total circular logic in that kind of sense. If one of these statements is true, they are all simultaneously true. If one is false, they are all simultaneously false at the same exact time. We often access these theorems by the easiest way possible, part D. Analyzing the pivots will tell you whether they're all true statements or if they're all false statements. And suddenly this theorem is a little bit interesting. We can connect it with some of our concepts so far. So we're pretty much done with the notes here, but examples 7 and 8, really just concept questions to connect more information. We're told in example 7, A is a 3 by 3 matrix with 3 pivot positions. So if we visualized it, it would look something like this. You have a pivot here, here, and here. And we're asking just right out of the gate, does AX equal 0 have a non-trivial solution? Well, theorem 4 is not relevant to that question, but, well, we have another theorem. It tells us if there are more columns than rows, there are non-trivial solutions. That's no good to us. The number of rows and the number of columns are equal. Anyone happen to know what the answer to this should be then without any theorem helping us?
They just have trivial solutions because they have equal rows and columns.
Absolutely. Because it has equal rows and columns, and because there's 3 pivots on this, there's only the trivial solution. So the pivots was the key as well. If we look into, or if we say it this way, since AX equals 0 has no free variable, because it's size 3 by 3 and 3 pivot positions. Well, maybe this is the better one to put in a box. It's all about the columns. Every column is a pivot column. And if you have 3 pivots, that goes together as concepts. That means there's no free variable. And so we can conclude there is only the trivial solution. we need a free variable to have the non-trivial solutions to do stuff like this, for example. X2, X3, X5 were the free variables in that system. Then another question that seems kind of unrelated. Does the equation AX equals B? So this one could be a homogeneous equation, just like this one above. But this is implying that this could be any vector that fits the size here. Does the equation B, this will have to have 3 entries in that vector, have at least one solution for every possible B? That's a lot to say there, but that's the same as this statement. For every vector B in R3 for this case, the equation AX equals B has a solution. Well, we connect that dot with, is there a pivot in every row? Yeah, there has to be. There's 3 rows and 3 pivots. So this is an automatic yes by theorem 4. We can just say immediately, since there is a pivot in every row, AX equals B is always consistent. So that's an okay way to answer the question. It asks if it has at least one solution for every possible B. That's synonymous with saying the system is consistent. Also, it was a question, right? I never said yes or no to this. So if this was your work, since there's a pivot in every row, AX equals B is always consistent, I would take that to mean you said yes. But if you're worried if you didn't put in the conclusion, it doesn't hurt to just straight out say yes. That way you can make sure you didn't miss answering the overall question just on accident, that your explanation maybe didn't contain the actual connection there. But that's how this one goes. Notice that this one, having at least one solution for every possible B, it's all about a pivot in every row. AX equals 0 having non-trivial solutions. This was all about having no free variable, which occurs exactly when there's a pivot in every column. So that's the reason theorem 4 is making a comeback. Having pivots in rows versus having pivots in columns might be telling you the same thing if the matrix has the same rows and columns. But if it doesn't, these are completely different concepts altogether. So the funner way to do this kind of problem, this is kind of like a warm-up, is to do it all over again when this system or the matrix A is not square, maybe 5 by 2, 2 by 5, for example. But any questions at all, folks, getting through this one? Okay, so for the moment, the big takeaway about all this is pivot in every single column is going to tell you there's only the trivial solution because there's no free variables. And yet a pivot in every single row is going to tell you the columns span all of R3 in this case, that AX equals B is always consistent. It always has a solution. And of course, every vector in R3 is a linear combination of the columns of A. So let's try this all over again. Different system this time. This is when the problem becomes a little bit more interesting. You'll notice a lot of concepts are, well, kind of redundant if the number of rows and the number of columns are the same. And that's the key to that gigantic invertible matrix theorem that we're going to take a look at finally in chapter 2. The theorem 4 excels with these kind of matrices when the rows numbers and the column numbers are different. This one is 2 by 5, so if this has been a helpful strategy, might as well copy it. 2 by 5 would look like this. My dots mean these can be any real number whatsoever. It has 2 pivot positions. It didn't say where they are, so I'll just generically say pivot here in column 1, pivot here in column 3. Because I circled it, it's a non-zero entry for sure, because it has to come out as a pivot upon row reduction.
We should add another column.
Sorry, say again?
We should add another column.
Yeah, absolutely. Thanks for spotting that, Demba. There should go 5 columns. Yeah, my counting was a little bit off on that. Thanks for spotting that. And I put a pivot in column 1, pivot in column 2. Excuse me, column 3. Counting's hard today for some reason. Other questions at the moment? Okay, so now let's run through those same equations. What would you all say to this one? Is there a non-trivial solution in this case? People in class have made a decision. How about for folks in Zoom? What would you all say? Yes, non-trivial, or no to non-trivial?
Yes, it does have a non-trivial solution.
Yeah, I totally agree with everyone. Seems like we're all on the same page. Has a non-trivial solution because, well, the x2, x3, x4 variable, excuse me, let me try that again. The x2, x4, x5 variable, counting still hard, in this system would all be free variables. Really all we have to say here is, well, there is not a pivot in every column. That would do the job. Or we could just say, since there are free variables, that's a better way to say it because this is just an example for visualization. Anything can happen with the pivots. There just is 2. That's all we know. Since there are free variables, there are non-trivial solutions. So that part's done. Next it asks, does AX equals B have at least one solution for every possible vector B? This vector would have to have 5 entries for matrix multiplication, excuse me, 2 entries for A times X to result in a compatible matrix equation. But what would y'all say to that? Would this always be consistent? Some in class are shaking their heads, yeah, and I totally agree. This time there's a pivot in every row, and that's just the content of theorem 4 above that we're looking at. If there's a theorem there is a pivot in every row, that system is always consistent. So we can just say, since there is a pivot in every row, yes, AX equals B is consistent for all B in R2. You didn't have to say B in R2, but just a reminder, if there are 2 rows, the right-hand side would have 2 entries as well. And over here, if you didn't say anything about the free variables, you might have said something similar. You might have said, since there is not a pivot in every column, that's another reason why we had non-trivial solutions. If there was a pivot in every column, this would be a different size matrix, it would have only been the trivial solution. So there's lots of interaction with what's going on with rows and columns, and there's going to be even more in the sections 1.7, 1.8 to 1.9. Lots of information is going to keep on coming back at us this way. Then in chapter 2, we'll do matrix algebra, and we'll see a special theorem where the number of the rows equals the number of columns, telling us a lot of information all at once, simultaneously. But this is a stopping point for these notes here. Any last questions or comments, folks, on any of these concepts, non-trivial solutions, parametric vector form? Okay, let's retire these notes finally. Looks like we would have been just fine to get through them if we didn't have a fire alarm that day. Now we're just kind of a little bit skewed on our time, so let's see how much we ought to do with this. We have about 10 minutes and some change. Let's maybe do example 1, and then we can call it a day. I don't want to go too far and break this over a weekend. It's sometimes a tough thing to come back to. First, I want to show you what the organization of these notes look like. We're talking about linear independence. And the way we're going to look into this is, I'm going to start with examples so we can see what's going on with linear independence, and then drop a theorem below after we work it through examples. We'll look at some more examples, this time with two vectors, drop a theorem below, repeat it with 3 vectors, and drop another theorem below. So it's kind of backwards with how we've done the notes in the past sections. The reason we're doing it a little bit backwards is this definition in this pretty much exact form is going to come back in chapter 4 in the most abstract way ever. It's going to come back in chapter 4 where this is just a vector space V, not Rn. Vector spaces are pretty abstract things. This could be a space of polynomial functions like x squared or t squared, depending on the variable we choose. It could be a set of functions like cosine and sine, and really it can be any mathematical object that satisfies a pretty long list of axioms that we're going to take a look into. So understanding this definition exactly as written is really fundamental, and that's why we're going to attack it from example 1, 2, and 3, first with what the definition says to get a feel for it. That's going to prepare us a lot in chapter 4. So first, let's take a look at this big definition. It comes in 2 parts because it's defining independence versus dependence. But first, there is a humongous connection, and this color coding is meant to match up for us. Homogeneous equations are kind of the key to defining this. Linear independence is saying a set of vectors, v1 through vp, so v1, v2 up to vp, all in the same space, Rn, are linearly independent if the homogeneous vector equation has only the trivial solution. So think in terms of independence, meaning only that solution and nothing else. We connect the next set of dots. This is why we were so concerned about non-trivial solutions in the prior problems. If it's not linearly independent, it's linearly dependent. And that means it doesn't have only the trivial solutions. It has a non-trivial solution. Our author wrote this in a kind of interesting way. Linearly dependent, if there exists weights, C1, C2 through CP, not all 0, and they could have been x1, x2 through xp, it would have been the same thing. I think he changed from x to c just to not have a conflict of notation, maybe. But when we say c1 through cp in this vector equation are not all 0, we mean non-trivial solution. So that's the next glue we want to put together in our mind. Linearly dependent is totally tied together with, you know that there are non-trivial solutions. Maybe the vector equation, well, if this will happen exactly when the vector equation has a free variable, for example. When that happens, we say that this equation here is a dependence relation, a linear dependence relation among v1 through vp, when we can find a combination of scalars or weights, not all 0. So that's a big definition. Our goal is to really understand this well. And here's how we're going to start. We're going to run the 0 vector in R through this definition to see just what happens. First, any questions about the definition itself? Okay. On either case, either way you look at it, you set up a vector equation, set it to 0. This is all about the homogeneous system we're studying. So we're going to take the 0 vector in R2. We could give it a name z if we just want a name for the vector, but it has to have a vector of only zeros. So here it is. Let z equal 0, 0. Now it's the 0 vector. Consider this vector equation. Well, there's only going to be an x1 times z because we only have one vector to consider. x1 times z equals the 0 vector. Well, this would have to have 0, 0 for entries. We're stuck in R2. We can rewrite this as x1 times 0, 0 equals 0, 0. If we did that, well, we can say, well, this is the same as x1 times 0 here, x1 times 0 here, 0x1, 0x1 equals 0, 0. And there's lots of ways to solve this, right? You could set x1 to 0, but you could also do this. This has non-trivial solution x1 equals, that's trivial. Let me try again. x1 equals 2, or you might have put 5, or square root of pi, any number that's not 0. If I put a 2 here, I found a scalar that's x1, I set to 2. It's definitely not 0, and it satisfies the original vector equation. You could just plug 2 there, and 2 times the 0 vector is still the 0 vector. This tells us the following. Therefore, z equals 0, 0 is linearly dependent in R2. Didn't have to say the in R2 part, but this is what linear dependence means. You can find something that's not 0 that solves a homogeneous equation. That is what gives us linear dependence. Any questions, folks, seeing it from the 0 vector side? So far, the concept is this vector wasn't special. Any 0 vector is automatically linearly dependent. And it doesn't matter if it's R2, R30, or a more exotic vector space. The 0 vector, as a theorem, is always linearly dependent. But what about this one? That is not the 0 vector. So your guess might be linearly independent, and your guess would be right. But it's instructive to see why linearly independent, just to learn this definition. It's important later on. So if we took, say, x1 times v set equal to the 0 vector, we're just looking at just one part here because there's only one vector. This would become x1 times 140 set equal to 0, 0, 0. So that's the same equation here, just written out. If we do the scalar multiplication, it's x1 for x1, 0 equals 0, 0, 0. So all I've done is do the scalar multiplication of x1 into that vector. But then you could say, if vectors are equal, the definition of vector equality is that the row 1 entries are equal, row 2 entries are equal. Row 3 entries being equal don't really say anything interesting. That's just 0 equals 0. But just to emphasize, let's put it in. But then what this tells us fundamentally is, therefore, x1 equals 0 and x1v has only the trivial solution. You just have to put in 0 there to satisfy the homogeneous equation. Because it has only the trivial solution, here's our big conclusion. Therefore, the set that contains the single vector v, I just have one vector, but you could write it as a set, is linearly independent. So that's what linear independence looks like if we run it through the equation. Does that make sense to folks on how this one works? Okay, we'll study this equation more when we come back to work on these notes more fully on our Tuesday's class. But the theorem that goes along with this is finally this down below. If you're only considering one vector, then v is linearly independent if and only if it's not the 0 vector. These theorems are going to be specific in how many vectors you have in a set, so I'll try to always emphasize that. That's pretty much the goal of our notes. Work with the definition, and then mention the shortcut. And then when we've done enough shortcuts, we'll do this. We'll visually inspect the vectors and just say, are they independent or dependent, depending on what we see going on. So we'll run through all those theorems again to see how it would apply in this kind of rapid fire, sort of like a quiz problem in the middle of the notes. But I think that's all I have for folks. I'm running out of time. Any last questions at all before we call it a day? Okay, well, have a great weekend, folks. We'll be back to this spot right here on Tuesday's class. Take care.